Hello. Hi. Apologies for the delay. I had a couple of issues with the internet connection and stuff, but we are all now set up and ready to start. And I'm going to share my screen so you can actually see what's going on. So this class is going to be focusing on testing data pipelines, and with a specific focus on what matter most, the code or the data. It will be a very, very basic introduction on why we would want to incorporate testing and data validation to our data-intensive or data science pipelines. Just to start with a little bit of me, I am a data engineer at Hello Soda, and part of my job is helping data scientists and other data engineers to produce better models that are more robust, more reproducible, and they can handle larger amounts of data. So I'm also very concerned with scalability and data availability issues. On top of that, I've also been working as a research software engineer, so also been working with researchers and academics in different institutes around the UK. I'm also a trainer and instructor for the software carpentry, for those that are familiar with it. I love everything around reproducibility. I'm also the founder of PyLadies Northwest UK. If there is anyone that belongs to the north of the UK, we now have a new chapter around here. Also an open source advocate. I am a community builder and a contributor and maintainer of different packages. And all in all, I wear a lot of hats. So if you follow me on Twitter here in Czech, you'll see that I do a lot of things around a lot of topics and a lot of communities. So we're going to get started with very, very basics and just some insights on data science. Probably most of you will be familiar with this or might already work as a data scientist. So one of the questions we have been asking ourselves for quite a long time now is, what exactly is data science? We hear data science everywhere in the newspaper, TV. All the companies want to hire data scientists. We have now more and more access to data than anywhere before or any time before. And this has created a surge and the need for data scientists across all sectors around the world. But there is still a huge debate about what data science actually means. And also there is also a huge debate about what a data scientist is and what tasks this person actually performs. But instead of focusing on technical skills or what tools or not tools someone is capable of using as a data scientist, I always like referring to this quote of DJ Patel, that is, the dominant trait among data scientists is an intense curiosity or a desire to go beneath the surface of a problem, find a question, and distill this into a very clear set of hypotheses that can be tested. And I like it because it focuses more on a mindset rather than on a set of skills or a set of abilities. And also it has like this very nice bit here that refers to hypotheses that can be tested. And that's why I focus so much on testing and testability and validation of data. So if you work as a data scientist, or you are an aspiring data scientist or an amateur data scientist, in general, we try and make discoveries while swimming in data. So data is our most valuable asset, but it's also can be very confronting and confusing when we do our jobs. In general, like data science workflow will be composed from these steps that are problem definition, data collection, and preparation of some sort, developing a certain model, deploying the model, and trying to do iterations to improve either the performance or add new features or retrain or recalibrate these models. This is pretty much like an idealized cycle on how this data science pipeline works. But in real life, it is not always a linear process or a one-way cycle, as the previous slide. Often when you are working with data, you define your questions, you find data, and then you realize that you have more data or less data than what you were actually expecting. So you have to go back and redefine the problem or define the question in a different way. And also it's very, very fluid. As you're starting to work on your predictive model, cleanse your data, present results, you can go at very different stages throughout the process of doing your data pipelines. Because these are not linear processes or one-way cycles or predefined steps per se, it is integral that at any point we know what we're doing with our data, how our scripts or how our models are performing throughout our entire pipeline, because this will make it more robust and will help us to identify a lot of issues down the line. So when people come and ask me, well, one of my parts of my job is to help work with data scientists and other data engineers to ensure that our pipelines are robust, that our models are robust and reproducible, and that we can scale properly. So often when people come to me and ask me what they can do to improve the performance or the reproducibility of their pipelines, I always refer to these basic sanity checks that comprise like just different steps of data analysis pipelines. So for example, when you're doing the transformation or your data wrangling or your data engineering processes, you can always check during the intermediate steps if you're getting additional or losing at null values, or you're getting strange values being added during your grouping or your aggregation processes. Also, you should be able to have a feel of what your data frame looks like, what the shape of it is, and identify whether during the transformation processes, this data frame is deviating from what you would expect to receive. Also, it is important to verify that if you're doing aggregation, let's say that you are aggregating a certain feature by its mean or the sum or another different measure, make sure that there are no duplicates of these aggregations. Also, you should be able to check, or it's advisable to check the interim or intermediate math and statistical results from run transform data. I'm going to leave it like that, but then I'm going to tell you about more what your raw data, should look like. Also, make sure that you have coherent data types. So often, I don't know, if we have two columns, for example, with a start date or an end date, and you want to get the delta or the difference of time between those two dates, you would ideally do a subtraction within those two columns. But for example, if we are a bit unlucky and it turns out that certain rows had these dates inverted, we would have a negative date. So we should be able to identify these data types or these data values that are a bit incoherent. And also should be able to identify what schemas are deviating from the expected ones. If we're still getting the expected or a sane schema or data type from our data sets. When it comes to the actual analysis or the actual modeling processes, something that should always be checked is the data normalization processes. Why you're normalizing the data, how this normalized data looks like, and what additional insights you can get from there. Also, depending on the models and approaches that you're using, keep an eye on your residuals, and if possible, do some visuals of your residuals, because this will give you a lot of insight as well. Make sure to double check your stationary time series, as well as the logical order of the operations. For example, if you're using something like Jupyter Notebook for exploratory analysis or reports, if you run the cells in a certain order, you will the processes or the functions will be evaluated in that order. But if you start skipping the order and go back, this cell execution can change a lot of your results. So you have to be aware of the logical order of the operations. Also, when people are working, for example, with Pandas, one of the most complex things to get a grasp of at the very beginning is this difference of shallow and deep copies of data. So have an understanding of what effect your actual processes or your functions have in your data, and what actual data pieces are being applied on. And finally, never touch your raw data. Your raw data should always be there, pretty much immutable, so that if at any point you delete all of your other interim or processed or finalized data sets, you will always have a way to refer back to your original data. A lot of people often start raw data, start doing manipulations, and move the data in place. And then if anything goes wrong, or it turns out that they need to roll back to a previous version of something, that data is lost. Also, when it comes to the data collection and ingestion processes, again, make sure that on the input and the output, you have a consistent schema. And when possible, evaluate the use of serialized data formats like R data if you use R, or pickles. These are very, very lightweight, but they're also very obscure. So depending on who you're sharing the data with or your models, and how much access to the regionals you will have, try and evaluate whether serializing or using serialized data formats is the most appropriate for what you are doing. And also be aware of the garbage in, garbage out so-called problem. Make sure that the quality of both your input data and your output data are well investigated and well kept an eye at all times. So I know a lot of people already do these basic sanity checks. Say, well, I already do this sanity checks, so I don't need to do testing. And probably the right way to look at this is to take these sanity checks to a bit more formalized process and transform that into your actual testing suite or your testing processes. It can be tricky, especially because testing data science pipelines or testing codes is very, very different to testing traditional software or other types of software. But it is not impossible. And often a lot of people say, well, why should I bother? If I'm developing, for example, my model, then more than likely this is going to be passed over to another software engineer, and he or she or them will do some optimizations or modifications and do the testing and then take that into production. But when you test your code from the very beginning, it's less likely to have bugs. This means that it will also speed up like the whole iterative process and deployment process of your model. Also, code that is well tested scales better. Meaning that you have from the very upfront a very clear idea of what sort of data and how much data your code or your model can actually digest. And you can start thinking of potential flaws or potential bugs and identify ways to improve or identify additional features that can be added to your pipelines early on. And this goes directly related to allowing you to iterate quickly. If you find a bit of a process that is lagging at some point or that is having a bit of problems, then it gives you the opportunity to react and do more iterative processes. And also, having validated data will avoid catastrophic failures. So many problems with the data, if you're having problems with your input data or your output data, they can go pretty much unnoticed. But because they go unnoticed and these errors are not 100% evident as a total failure of your code, for example, or your model, sometimes these can lead to very bad decision making or I don't know, poor performance of your recommendation systems or worse. And also, when you start testing all of your data pipelines early on, that means that it will reduce the manual load that you will have to do later on in the processes. So usually I like using test-driven development. I like using test-driven development for data science, and this is basically start thinking early on about how you're going to develop your code, how you're going to develop your model, and how you will start testing it from pretty much the very first minute. And in order to have a TDD approach, you have to start with pretty much preparing your environment, making sure that you have all the tools and all the information to do so. And then it starts with modularizing, for example, your code. If you have identified different functions that you're going to be using repetitively, or there are some tasks that you need to perform a few times, consider modularizing your code, making functions so that this can be more portable and reusable. Also try and make it safe to rerun the job. Make sure that the data still exists, or if you're using something like AWS or E3 instances or buckets, make sure that the address to this instance is valid, that it is still there. And also consider whether you're going to push partial results to, I don't know, again, these cloud instances, or if you're only going to push the very last result. Also, when you are developing your own models, make sure that you don't hard code paths, because this makes particularly hard to share your code and what you're doing with other people. Imagine this very typical scenario where you have a very cumbersome file system, for example, Tania/data science/client/awesome data model, and things of the such. So if I want to share this with my colleague, more than likely them will have a total different file system or different file path. So if I import all of my data and all of my models relative to my path, this person will have to do a lot of manual labor to fish these paths and correct them. Also, timestamp and version your data. It's also a very good practice to know what data set or what version of your data you are using, for example, to test or to calibrate or to train your models. Also, when we're developing models or when we're developing data pipelines, we normally start doing this in our local computer. So we normally start doing unitary tests, or testing our functions, or testing our models, or testing our data acquisition processes locally. So that is the first approach that we should aim for. And also this will allow us, if you're using, for example, a faker or a helping package to create fake or synthetic data, you might then start identifying problems that you don't have probably enough data sets or enough data observations, and by doing this locally, you can have a better idea on how this will look later and how your model will perform later on in production. And also need to identify edge cases. Sometimes when we are testing locally, we test for 1 or 2 cases that we know that our model will or will not fail. But one of the very important things when we're doing data science or when we're working with, machine learning or predictive models or recommendation systems is identifying these edge cases at which our model will have a very different or unexpected behavior. And so far, I have focused a lot about the code and how do you test the code. But just as important as testing the code is validating your data. Because at the end of the day, the data is our number one asset, is our first-class citizen, and it's also our output, is our final product. Normally, it's not going to be the model itself, but the data and the insights we can extract using that model. So we should be able to think and identify where is that our data or our process is going to fail, and what are the possible cases. The data is, well, especially when we're working with real world data, we will have less control on some of the features or on some of its characteristics. Also, you can assess how difficult these malfunctions or misbehaviors of the data are to sort out. For example, missing data or missing values are not as hard to take care of during your data models or during your analysis, and you can kind of control a bit the number of missing values in some cases. But then when you think about, schema changes, so many of the schema changes come because of problems during your pipeline, problems during the collection methods. They can also lead to corruption of your databases or your data sources. And the ones that are like very, very far away from your control are possible bugs, or just, again, unexpected behavior of the model or the code or platform or the infrastructure, as well as some biases that may occur during your modeling. And all of these different failures or different of misbehaviors of your model and your data can be caught early on, keeping a bit of track record and validation of your data at different processes or different steps. So as a general rule, we should always aim to have both a validation of our inputs and a validation of our output data, because this will allow us to make our pipeline very robust and identify a lot of these issues very early on, rather than finding out about these issues when our model is in production, or worse, after it has been rolling for a few months or for a couple of years. So basically, when you do the input data validation, it is important to do it, because when you have a bad input, this will more than likely degrade or reduce the output or the quality of your output. And it is also very likely to pass unnoticed, as I mentioned very early on. If you have a malformation of your schema or some corruption of your data, most of the times you won't notice, because you will still get some data ingested. But if you do this early input data validation, you will be able to detect pathological data and its failures very, very early in the process. And it will also give you the opportunity to deal with expected data variability, should be able to identify which is inherent noise or inherent variability of your data rather than external artifacts. And this initial validation should allow you to deal with this easy to control medium difficulty artifacts that I pointed before, such as missing values, encoding issues, schema changes, data order changes. In addition to validating the data itself, we should always aim to validate the metadata, which is essentially data about the data, because this will give us lots of information from our sources and what we should expect from our data. And when it comes to output data validation, it is important because we humans make mistakes. At any point, we're going to make a mistake, or a colleague will make mistakes. And it is very easy that these are propagated down our modeling pipelines or down our entire services, for example, or products. So once you have ingested your input data, done all of your data engineering bit, modeling, prediction, labeling, or whatever you're doing, before returning the output, you should also validate it. Generally, you should check for anomalies. If you're using, for example, supervised machine learning methods, you can use a validating data set along with a certain confidence threshold to identify whether your model is behaving as expected. And again, check for edge cases. Make sure that you're not going far beyond the capabilities of your model. So we're going to start doing some practical work, or I'm going to work on Jupyter notebooks. If you want to follow along or get the material, you can use this link. It's a GitHub repository, and if you click on the link, you'll get all of this. You can download it. Well, you can clone it for now and follow along, or you can just follow along with what I do on the Jupyter notebook, and then the materials will be there for a very long time, so you can always go back and refer back to them later on. If you have also any questions, we have the chat. Well, yeah, the question chat, so I'll try and keep an eye on it just to make sure that I don't miss any questions. Okay, so we're going to start with this Jupyter notebook. If you're not familiar with it, for example, I'm going to rerun this. Can you see my terminal? So if I go to, oh, okay. So someone is having a problem with the screen. I'm gonna try and unshare it and see if the resolution improves. Is this any better? Oh, okay. So apparently some people can see a clear screen and some others can't. So yeah, you might need to play a bit with the resolution directly on YouTube. Thank you. Oh, so I'm going to start, with testing 101. So if you have cloned the Git repository, you should be able to start with this testing 101 notebook. So I've so far already mentioned a lot of testing, or that you have to test your code. So if you have never written a piece of testing or any similar thing, there are different levels at which you can test your code or you can test your data. So you can start, for example, with assertions, which is a basic testing, meaning that you check, well, unicorn equals unicorn, or you're basically comparing one-to-one some things. You can also then check for exceptions, and this normally go within your code and a service warning. So it will identify possible bugs or possible failures or possible things that are not likely to work. So this is a bit of like defensive programming or defensive testing. Then we can also test every single piece or every unitarian piece of our code. Let's say that we have a certain model, and in order to go through the model or go through our entire pipeline, we have 40 different functions that we wrote in Python. If we do unit testing, it means that every single one of those 40 functions will have some sort of testing or some sort of verification. Then, for example, when we have our entire pipeline and our model and we have put it all together, we can test the entire pipeline and say, well, is this output actually what I should expect to see? Does this make sense? Is it working appropriately? So by putting all of these unitarian tests or these unitarian parts together, we can identify bigger issues or possible bugs during our models. And this integration test in combination with the regression test gives us very, very robust metrics on how our model is performing. So I'm going to start with an example of an assertion. So let's say that we have been given this task at our work of writing a function that can identify if a given number is a multiple of 5. So you go ahead and then you write this function in Python that is, we're going to call it is multiple, and it takes an argument called number. And then we declare this variable that is going to be set to false or to true, depending on whether this number that is being passed is a multiple of 5. So let's say that we use the operator modulo, that in Python is going to return us the remaining of a division. So if we divide the number by 5 and the remainder of this division equals 0, then that means that our number is divisible by 5. So if I pass, for example, the number 15, then I receive a true, meaning that it is a module. A multiple of the number 5. So you have already completed your task. You are 100% sure that your boss or your colleagues are going to be very impressed, and you walk away. And you send this to production. You send it to your production team. But probably it might not work, because there are going to be some cases in which your function doesn't really work. Let's think about the case of the number 0. If I pass the number 0 to this very same function, it will going to say, yes, it is a multiple of the number 5, which, well, strictly speaking, it shouldn't be a multiple. So in Python, we can use this library or this package called PyTest, and it helps us to write tests with very little lines of code. It is much easier. It is much more approachable than unit testing, and you can pretty much just start writing simple tests for your functions straight away. So I'm going to go back to this function just to remember how this is written. What you can do now is declare a def, another function that I'm going to call, in this case, test is multiple. So I just prepend the word test. And then I know, well, if I pass the number 5, then its multiple should give me true. If I pass the number 50, it should be true again. If I pass 0, ideally, it will give me false. And then if I pass -10, it should give me false. So if I run this function, PyTest is going to evaluate these cases. It's going to pass these different numbers to your function and assert if what is going to compare one by one. Remember that I mentioned that this assertion is comparing 1 to 1. So it's going to compare whether what I'm getting back from my function equals what I'm saying that it should return. So in this case, it goes through 5, it passed the test, goes through 50, it passed the test as well. But then when it gets to number 0, it is returning wrong value, which is what we had here. So then, now knowing that we are having these problems, we can go back and rewrite our function. So instead of just verifying whether my number is divisible by 5, and the modulo or the remainder of the division is equal to 0, we can add this additional condition saying if my number is greater than 0 and the remainder of the division equals to 0, then it should be a multiple of 5. So if I pass my number 15, it is working. And then, because I have already written these test cases, I can call again my test function, and PyTest will again pass those these different conditions. Since we didn't have any explicit warnings or any explicit problems, we can go away and assume, we have now, the assurance that all of these test cases passed. And you can write as many as you want. Let's say I'm going to say 100, and it should be true. And if I pass this again, this test should still work. This is a very basic example, but you can think of pretty much any function that you are writing and write similar tests for this same function. Now, the only problem is that you are testing for very specific cases. In some occasions, these very specific cases are much more than enough, are sufficient for what you need. But in some other cases, you will probably need a more robust or or a broader testing scenario. And hopefully, we will have time to go over that in a bit. Then the next thing that you can introduce as part of your pipeline is the exceptions. So basically, we're going to catch bugs before they are bugs. So now imagine that on your daily workflow, you want to load a data set. And in this case, the data set is the 1MAG data set from Kaggle. So probably you were working the other day on this data set and you downloaded it and you had it on your laptop, but then this day you're working on your corporate computer and you completely forget. So when you try and load this data set, it's taking a while. So when you try and load this data set because you've not downloaded it to your personal computer, Python and Pandas is going to complain because this file doesn't exist. So something that you can do, for example, in order to avoid these kind of problems is add directives like this. So it's going to be in a 2-step, but it's going to perform the same tasks. So you can say, okay, Python, try and read this CSV file in this local directory. If it fails, or if it throws an exception like this, that is file not found, then use this URL. In this case, I am using the version that I have in my repository. And this way, Python didn't complain, so we prevented this error even before this happened. And this becomes extremely useful when you are working with data sets, or you are generating, for example, a report, and you want to make sure probably that you're not overwriting an existing version of something, or that you're not overwriting another report, or that you have the appropriate file system. But it helps also a lot when you are going through your data sets and you want to make sure that a certain variable or a certain feature exists as well. And if it doesn't exist, or if you can't pass that to another function, then you will have a fallback plan or another behavior. So I just did, well, I have loaded my data set now on this variable called df, and I'm just gonna, I just did a df head so I can see a bit how this looks like. So we have different columns that tells us about the country of origin of the wine. This data set is particularly, well, is located in Kaggle, but it refers to a certain number of people or Twitter users that reviewed or provide reviews to a number of wines from all over the world, pretty much. So the kind of data that you have in this data set is the country of origin of the wine, the description that was provided by the reviewer. So you have things like, I don't know, tartness or flavors. Some people have included, I don't know, which kind of food the wine pairs well with. Also, it includes details on the designation. A vast majority of wines will have a designation of origin, so that is captured here, and has points, prices, which provinces in this specific country it comes from, some regions. It also has information on who was the taster or the reviewer, their Twitter handle, and the winery. So you have a lot of information, but most of this data is, as you can see, text-based data, or strings. We have very little numbers in here. So this brings us to this actual part of data validation that I was talking about. And the very first thing that we can do is making sure that we are actually getting the kind of data and the format that we're expecting. For example, if I'm talking about designation, it makes sense that we're going to have the name of a vine, of a grape or a vine. So you wouldn't expect to see here data types of this, I don't know, like dates or floating numbers or integers, but you would expect to see a string. And the opposite is true for price. You would expect to see a floating number or an integer number. In some cases, you will have data sets that are passed as a string because they will have the dollar signs or the pound signs or the peso sign, depending on the localization of your data set. But it's good to know from the very start how your data should look like. And we can do this by doing some schema validation. And for this, I'll invite you to refer back to JSON schema, which is basically the guideline on how a schema should be formed. Luckily enough, there are a number of Python libraries that can help us to do the validation of these schemas so that we don't have to do it by hand, or we don't have to write our own functions. So packages like this are Schema, Voluptuous, and Cerberus. And I, when possible, use Voluptuous because it's very flexible, it's lightweight, and it's rather intuitive. So if you don't have Voluptuous installed and you want to try it now, you can do a pip install Voluptuous, and it doesn't take much time to be installed. So what does this schema validation mean? As I said before, it refers to checking that all the fields are there, that the columns, I don't know, that the name of the reviewer exists, that the types are understandable, and if they're understandable, they'll be parsable by my computer and will be so to work with. So Pandas allows us to directly see the data type of our data frame. So if you do df, which is, if you remember, where we loaded our data set in the form of a data frame, if you do df.dtypes, it will display the name of the columns and what kind of objects or what kind of data you have in that column. We don't have data here, but Pandas is very good at dealing with and decoding and parsing dates variables or dates values. So we can start. I'm gonna remember that I'm gonna be using Voluptuous for this. So we're gonna start with a toy example of a given schema. You import from Voluptuous, import schema. If you click on the links that are on the notebook, it will take you directly to the GitHub repository of Voluptuous, and it'll have the documentation if you want to refer back to it later. So we're going to start with a toy example. So we're going to call the library. So from Voluptuous, import schema. It's capital S. And we're going to define this schema S. We're going to pass it in our JSON format. And we're going to declare a key called Q. And I want it to be a string. And I also declare another variable called per page. And I want it to be an integer. And the same goes for page, that is going to be an integer. So let me split my cell. There you go. So if I evaluate my cell, nothing happens. But then I can, if I print S, you can actually say that it is an object, and by default, it generates this meta class. So it tells you the Q is class string, per page is a class integer, page is also class integer, and this extra, prevent extra, means that these are all of the fields in your schema. So if you pass something that doesn't exist in the schema, it's not going to pass the validation. And then also, we haven't marked any of these as required. So this can or cannot be present. But for example, if you want to define a schema that always has the queue for a query, then you can mark this variable as required. And this gives you a lot of flexibility if you are working, for example, with a lot of data sets that have certain fields in common, and that are always going to be present, but then you have others that are not always there or a bit flexible. So then you can think of like a base template or a base schema for all of your data validation. So imagine that I have these data. I'm actually going to so I have this JSON object, and the value for my key Q is hello. Sorry. So if I pass these to my schema, it just does this is doing the validation or the in-place validation of the schema. So what it does is it checks for a Q, then refers back to this schema class that I created before, checks the value, and those checks if the fields are conforming. What happens if, for example, I pass this data object that instead of having Q, just one value or one unpacked value of Q, and I pass Q hello page world? The schema is going to complain because I declared that the field for page is an integer, and in this case, I'm passing a string. So if we go through these traceback calls, we can say multiple invalid expected integer for dictionary value at data page. So if, for example, I substitute this with a for, it should pass again. What happens if, for example, I pass an additional key that I didn't declare in my schema? Let's say that I am creating, I don't know, a URL key, and I pass Google. Again, if we follow the traceback, if we follow the error messages, it's going to say that there are no extra keys allowed. Because when we defined our schema originally, we said these are the maximum number of keys, or the maximum keys that are allowed. So if you add any additional, the schema validation is going to fail. So if we return back to our data set, we remember here we have all of this different columns. So we have, again, country description, price points, region, taster Twitter handle. So we can generate the schema. There are, you can create this schema, I don't know, manually, but there are also some libraries that can help you to define your schemas. I can't remember the name, but if I'm going to paste the link, sorry, to a couple of libraries that can help you to create your schemas from Python. So some of these libraries are fairly intuitive. So you have to initialize your schema object, pass, for example, your CSV file or your JSON object, and it will do a lot of, it will infer and parse your data and identify for example, how your missing values are passed as is if it's just an empty value or an NA or the -999 or something similar. So we're going to generate a very small schema for our data set that we had here before. And we're going to create a df schema just to recognize it, that it belongs to our data frame. We're going to declare the entry for country, that is a string, description, designation is a string, then price is an integer. I say that it is here an integer, for example. And then the province and the taster name. Probably these are the only features that I'm going to be using and the only features that I care about for the moment. But I know that probably I'm going to pass more features. Is a dataset different from a database? No. Well, a database is a collection of data sets, or it's quite big. For example, if you have things like SQL or Mongo, you can do queries directly from there and then get a subset of that very big collection of your data set, of your database. In this case, this data set is one of these subsets of data. And we got this in CSV files. So normally you can have a CSV file or a text file or HD5F or a JSON single file. Does that make sense? Okay, I'm going to assume that makes sense. But you can also, if, for example, you are working with big databases, let's say that in your work or your company, they use Mongo, and you are constantly extracting data from the database. Yes, they work similar. Yes. Yeah, so the schema is just, you can use it for your whole database, or you can use it for smaller data sets. And it helps you, as I said, to define the key values, the key and values that you should expect to receive. So as I said, if you have your database and I don't know, what was I saying, like MongoDB or SQL or something similar, and you're constantly pulling data from there to pass on to your models, you'll still have this schema that will validate these requests of data or this inflow of data. So yeah, in this case, I'm defining this schema. So if I evaluate my cell, my schema is already created. So if I do df schema, we'll see the same similar classes to the ones we saw before. In this case, we have allowed extra variables. And I'm not going to pass the whole data frame, but I'm going to just I'm going to take the first row. For example, I'm only going to take the first row of my data frame. So I do this by doing a slice, and I'm gonna save it in the form of a dictionary. So if I print this sample that I'm storing all of this first row dictionary in the form of, in this variable called sample, you see that it's taking the very first observation. So now I can pass this first observation to my schema, and we get a problem. Because it says expected integer for dictionary value at data price. So if we refer back to here, we actually see that the price is not an integer, but a float. So then you can go back and declare this as a floating number. It's updated. And if we pass this on to my schema, then my schema is validated. And we have a greater confidence. As I said, I only took the first row of my data frame, but you can do this for all of your data set, or for all the queries that you are performing from your database. And once you have done this, you have the very first validation and the very first layer of confidence on your data, and you know that you are getting what you should be getting. And you have to worry a bit less about the quality of your data and in your intermediate steps. So then going a bit further down the validation, we can start looking at missing numbers and duplicates. So we're going to start with the duplicates. I'm going to split this cell again. So in this cell, I'm going to print the total number of examples, that is the total number of observations that my data frame has. And I'm also going to find those examples that have the same title and description. So the title is the title that the reviewer gave to the actual review. And the description, in this case, for example, for the first observation, is it tells you about the quality of the wine, the taste, as I said, what it pairs up with. So if I get the shape, I'll get the total number of observations or reviews I have, and then if I use df duplicate and pass description and title, I can identify how many of these observations have the same description and the same title. So in total, I have nearly 130,000 different observations or different reviews, and we have 9,983 duplicates. But what about if we don't care about the description and the title? Because it's probably it can be likely that multiple reviewers just use the name of the wine and the year to create the title of the review. So we're going to focus on the description only. That is going to be a bit harder to have identical reviews. So actually, we're getting 10,000 reviews with the same description, which means that probably some people were a bit cheeky and changed the title, or probably they submitted a review and then decided that the title was not one they were happy with. But at least we know now that we have a considerable chunk of duplicates. So I'm going to start doing a copy of my data frame, because I don't want to mess up with my raw data. So I'm just going to create a copy, and I'm going to name it interim. I tried to choose self-explanatory name, so I actually know what my data refers to. So I'm going to do a div copy. So I'm going to df.copy, and I'm going to use the same method that I used before, a similar method, to the one I used before, but instead of passing duplicated, I'm going to do drop duplicates, and I'm going to subset based on the description. Now that I know that I have a good number of duplicate descriptions, and I'm going to say in place true, so that this copy has actually this function applied to it. And after this, I'm going to get some visual insight. So once I have dropped the duplicates, what I'm going to do is I'm going to get the number of rows that this new data frame has, and print some details. So we have now total unique reviews of 119,000, almost 120,000, and we're using Pandas description method to get some descriptive metrics. So we're applying this to the variety. If we remember, the variety is what kind of wine was being evaluated. And we say, well, out of these total unique reviews, you have 707 different varieties that are the different kind of wines. And the one that has the greatest number of reviews is Pinot Noir. And the frequency of this one is 12,277. And someone said that schema validation is very cool, and I love schema validations. I'm very happy someone does as well. So yeah, now we're getting a better feeling of our data. We get a better feeling of how much unique data we have, and what we can do about this. But I have already dropped all of these duplicates, and well, I can have a certain level of confidence that my data conforms to a certain standard. But what if I want to do some more checks? Because here I did drop the duplicates, but what if I, because I was typing very fast, I subset it according to variety instead of description. So then you can do some additional checks. And if we remember back to our assertions, if you remember, the number rows interim is the interim data set is that without the duplicates. So I can say, hey, Python, can you check if the number of rows of my interim data set equals to the original number of rows minus the number of duplicate rows? And we stored here the number of duplicates. So then Python will assert it and say, well, yep, this is what you would expect to get. So we're very happy up to now. We have already done a good deal of validation, and everything looks very nice. But we have not checked our missing values. So I'm going to split the cell, and I'm going to do So I'm going to do a total. I'm going to check those null values that I have here, and then do a summation and sort them by ascending order. So that way we can see on each of these columns or on each of these features which are the features with the greatest number of missing values. And we can see that the region 2, that is like the secondary region of which the 1 comes from, has the greatest missing values. There are no missing descriptions, there are no missing points or title or winery. But we have like the greatest amount of missing values when it comes to designation region. So it's like the localization of the words. But sometimes it is useful. If I look at these numbers, I can think, well, 79,000 is a very big number. But sometimes it is useful to compare these missing values against the total size of your dataset or your query. So for these purposes, we can create a percentage value of these missing values. So I hope it's not very cumbersome this. But we take again this is null that is checking for the NAs or the missing values, and then we get the percentage. We sort them by ascending again. No, we're gonna sort it by descending. Sorry. And then we're gonna create this additional missing data. This additional missing data variable where we're gonna concatenate this total percentage. And we're going to collapse it again. We're going to collapse it in the direction of the rows. So we're going to have the missing data per column rather than per row. Because this axis 1 can sometimes be very confusing. So if you think that this is the direction in which we're collapsing our data, it's looking at all of the observations on the rows. and we're displaying it in total and percent. So this total that we had here before becomes a bit more understandable, and we say, well, out of the total unique values that we had before, these missing values correspond to the 61% of our data. Okay, I'm gonna leave that question for a bit, but yes, there is not always straightforward, but there is, yes. So here we can start seeing how percentage of my data is not as reliable. So we can see that the most missing values are in region, destination, taster name, and price columns. So we're going to do this, and we're going to drop those columns that, or well, those rows, sorry, that don't have the price. I'm going to later on share a full data pipeline, so you can actually see, for example, what Alan was asking on how you would validate the pipeline in the intermediate steps and how you would pass from one process to another. So at this moment, I'm only doing the parts of data engineering, but all of this applies directly later on to the whole pipeline. So what I'm going to do at this point is drop DNAs. I'm going to get rid of those values that don't have a price, and then I'm going to reset an index. So this is how my data looks like. It's just the first 5 rows. And if I look at this, that is the new shape of my interim. Now I have a different number of rows. Let's say that, well, probably I'm not very interested in all of this data, but I only want to look at what are the top 20 wines. So I can do a count of the varieties. Unsurprisingly, Pinot Noir has the highest number of reviews because probably it's the most popular wine, but we saw that before. And we're going to subset it. We're going to take this on the 20 top. So we're going to do a cut on the top 20 wines. So I trust myself, I do it, and now, for example, if it's my lunchtime or the end of my day, I can leave work and I can just chill. And I am 100% sure that my data manipulation has been done right. But after a lot of years, I know that I make a lot of mistakes. So I'm not 100% sure if I can trust my data. And we can also use another nice method that Python comes up with, and it is to assert instance. So at the beginning, we did our validation of our data with a schema. Then we did all of these misbehaves or noisy data points controlled by identifying duplicates, or you can identify outliers or the NAs or the numbers. But then you can do an intermediate check because probably I have finished my data cleaning or my data engineering here, and I'm going to pass to my model. So I want to make sure that actually what I'm getting is a data frame. So I can test and say, well, Python, I want to check if this data frame interim is a Pandas data frame. Yeah, again, Python didn't complain, so that means that this assertion is true. So interim is a data frame, but we already knew that because we printed it before. And then my top wines, that's where I only took the 20 top wines or the 20 most reviewed wines. I also want to check if it's a data frame. Oh, well, it doesn't display an assertion error, but then this means that it is not a data frame. So I can go back and say, well, I am doing I am checking from these varieties that I have here. I am checking, and then I'm only taking the 20 top ones, but at the end, I don't know, I just added that to JSON because probably yesterday I was working with pipelines that were returning data as JSON objects. So I go back, I correct it, and now when I run my assertion again, Python is happy with it. What happens, for example, if you have a data frame, or you have a JSON dictionary, or you have something that you have passed through your processing or your data engineering pipeline, and you want to do some additional checks using Pandas. Sometimes when we have previous versions of the models, we have persisted copies of the data, or we have previous versions of the data. Probably we have a pre-existing version of this interim that I created before that is called fixtures. So I should be able to refer back to that. Let's say that is like what my data should look like, and I can compare if I am doing it right. So I'm going to load this fixture on dataset, on a data frame called fixture, and I'm going to call fixture.head just to see how it looks like. So it is again our very well-known data frame and data content. But Pandas has its own testing module. In addition to Pytest that we have been using so far, we can use the testing module. And there are a couple of things that we can check. We can check if two data frames are equal, and it will check all the observations. It will check for the indices, it will check for the number of observations and the columns that you have in there. Or then, if you remember here, I did a drop, a reset index. So sometimes you only want to make sure that you've not done that when you shouldn't do it. And you can check, for example, assert index equal. So again, I'm passing Panda testing or PD testing. Sorry. You can pass Panda testing, assert again, frame equal, pass the top ones, and my fixture that can be probably my persistent data set. Or I can say PT testing, assert index equal, and I'm just going to look at the index. So I run it, and it's gonna, sometimes it takes a bit depending on how big your data set is. Pandas is not very happy, so it tells us data frame index are different, and it actually tells you how different they are. In this case, it's really, really bad. So basically, every single of my indices are wrong. And it tells you the left, which is the one you declare first, the one on the left. So your top wines data frame has these indices, and the right data frame, that is my fixture, has a total different range that starts at 0 and stops at 81,464. So the length is the same. At least we know we have the same number of observations. More than likely, what I did is I forgot to reset the index here. So then I can go back and I'd say, well, now I want to reset my index. I want to drop it and do it in place so that this takes effect on my data frame. And now I can go and assert my indices again. And Pandas and Python are much happier now. Okay. Are there any questions here so far to what we have covered? I hope I'm not going too fast. if it's too fast or you have any questions later on, you can always drop me a message or an email, and I will be more than happy to discuss any of this with you. So if you remember at the very beginning, I did this testing here. And we define these very specific test cases. So there's 5, 50, 0, 10, or 100. So they're very, very specific test cases. And in so many occasions, we don't know what data or what data values we're going to get. So sometimes it is worth to have some property-based testing. And for this, there is a really, really good library called Hypothesis. And Hypothesis is basically allows you to identify the edge cases. You declare, in this case, instead of saying, well, I want to pass just these values, I want to test for integers greater than 5, greater than 0, and up to 1000. So what Hypothesis is going to do is take a sample of values that conform to this definition that you are passing and run lots of tests. So it's going to run as many, well, I don't remember exactly how many tests it gets, but it runs many more tests than those you can probably write manually. Okay. So before we use our modulo operator, because we knew that it existed and we've used it in the past. But what happens if we don't know that it exists and we're giving again a similar task, but instead of the number 5, we have the task of identifying if a number is divisible by 11. By 11, so we go and we don't know how to verify if a number is divisible by 11. So we find this property in the maths book that says that a number is divisible by 11 if and only if the alternating in sign sum of the number digits is 0. So we can create a main script, but I'm gonna create just the function here. It's probably we're not gonna have a lot of time, but I can create my function here similar to what I did before. And I can say divisible by 11, use this above criteria, and then I pass my string number, alternating some things of the such. And we can demonstrate that this works for numbers between 0 and 10. So we pass these numbers to this, and it checks if it is divisible by 11. Now, so it takes the sum of the number and then alternates the sign. So if we pass this range of numbers, it will do these operations and then it works. So we can do the same thing that we did for the original function, and we can do import PyTest and test this divisible by 11 function that I created before. And I can use the same for loop that I have here using my range 10. And I'm going to say assert if the number in there is divisible by 11. And you pass the number 11 times whatever number you're getting here. And you're gonna, so if I run these tests, it works. But I did a lot of cheating here because I already knew that all of these numbers are divisible by 11. So since I already knew, I wrote my test cases for those cases that I knew that my functions were going to work. But that is cheating. What if someone then comes and say, well, I want to test more numbers? At this point, I could probably say that I am a very good programmer, a very good data scientist, and leave my work and go have a beer or wine or just chill. And And most of the cases in research or data science, things are going to change. So we're going to import this library called Hypothesis. And we're going to import this specific module called Given. That is the module that actually allows you to define your inputs, as I was saying before. And we're also going to import hypothesis strategies as strategies. So this Given module actually works as a Python decorator. If you've never used Python decorators before, they can be identified by this arrow base or @ symbol before. And you instantiate, you started with its name. So say given, and then I'm going to use the strategy called integers because I'm only testing for integers. I'm going to say that the minimum value that I want these integers to take are 1. And from on here, hypothesis is going to decide on the values that these numbers are going to take. So now if I pass test divisible by 11, and I pass this number, instead of passing the number k that was in the range, I pass this number that is going to be generated by hypothesis into my assertion. Oh, sorry, I don't have hypothesis in this environment. But this is what you would expect to see. You would expect to see that it failed at some point, so it tells you why. And when it reached the number 28, that probably I wouldn't have thought of sending, I got an error. So when this happens, it is because 11 times 28 is not divisible by 11 if we follow this mathematical definition. But then we can use another definition of divisible by 11. Where did I leave that? Okay. Yeah. There was a typo. Oh, there it is. So we can now use this definition for a number to be divisible by 11. That is, if only the alternating and sign sum of the number's digits is divisible by 1, and we can modify it. So then if we decide this, and then I run again the same function using this test using hypothesis, it should not pass. And it will say that it ran one test, but you can enable the verbose section of hypothesis, and it tells you how many test cases it did for your function. Sometimes it does like 1,000. I think you can set a maximum number of test cases that you can pass per function. But you can see that this tests for many, many more cases than what we originally thought or what we originally imagined. And this is very, very helpful when we are doing data, like very data intensive modeling, or if we use other packages like Faker. In some cases, Faker is great, but you have to create many, many different synthetic data sets. Using hypothesis in conjunction allows you to maximize the reach of your tests in your data pipeline. Then going back to Alan's question, that is, for data pipelines that have multiple steps like one system feeding data into another system, is there a straightforward approach to testing such a system? What I've done so far here, that I defined my function and tested and defined the test per function, is unit testing. So you would normally start by getting a similar approach, that is writing a unit test case per function, and then have these intermediate steps. If we do schema validation, you can do a schema validation when you ingest your input data. And then when you pass it from one system into another, so you can do your intermediate data validation and then your output data validation as well. And you can test pipelines as a whole as well. If you do integration tests, you know, for example, that the first bit should give you a certain score or a score within a certain limit before passing on to the other one. And then test again that bit. And then you can do pretty much A/B testing is a fantastic kind of tool that you can use. For example, if you have a model, you can say, well, I have this model that consumes a parameter A, a parameter B, and a parameter C. I'm going to run this model with the 3 parameters equal to 1. And you evaluate what you get after that pipeline. Then you can say, well, now I'm going to set my parameters to 1, 2, and 1, and run against your pipeline and see what you get out of a result. So that is like parametric testing or A/B testing of your models. And that is very, very helpful as well to identify ways in which you can optimize your models. I knew we have very, very limited amount of time. 2 hours is not too much to cover all of this. But hopefully this has given you a nice introduction and a nice series of tips on what you can start doing to test and validate your data and your data pipelines. If you keep the link to the repository, in a couple of days, I will upload a whole pipeline that will cover this processing, the data cleaning, and then the modeling and some data visualization so that you can see how you would integrate a whole pipeline with these testing strategies. And as I said before, if you have any questions, you can always drop me an email or you can reach me on Twitter. My messages are open. Sometimes I take a couple of days to reply, but I always reply. Or you can, if you are familiar with GitHub, when I update things here, you can go to issues and create a new issue if you have any questions or have a bit of curiosity of, well, how do you integrate, for example, A/B testing in this? Can you add an example when the whole pipeline is added? I think we have an extra 10 minutes or so. So do you have any questions? Yes, you can use hypothesis to test the functions or the intermediate steps of your pipeline. You can use it. Yes. If you want to know, and this is a whole different approach to testing, and it's called property-based testing. So you can always you can always Google and try and learn a bit more if you're interested in them. But yeah, you can. It's mega useful when you're trying to identify edge cases for some of your functions or some of your processes or your models. Excellent. More questions? Complaints? Any suggestions? Okay. I hope you enjoyed learning a bit more about data validation, and basic testing. As I said, you can contact me at any time. And thank you very, very much, Karin, for everything, for setting all of this up, and all the amazing things you do with PyLadies Remote. And if anyone is in the UK or around the UK and are going to PyCon, feel free to reach out and say hello. I'm going to be in PyCon UK. And I'm always super happy to chat about data and Python and all things related.